All right, everybody, we're going to get started with our 225 presentation. Go ahead and grab a seat. My name is John Ziola, if you guys haven't seen me earlier. Thanks for coming out. This is it's turning into a really great event. So thanks, everyone, for making this such a great event. I'm going to be introducing John Downey. So John Downey is the security lead at Braintree, which I'll tell you a little bit about. Braintree helps businesses accept payments online and development tools with great development tools and first-class support. One interesting note about him is what he likes to do in his free time is contribute to open source projects, and he helps high schoolers build robots. So that's pretty cool, and I'm really excited about this talk. I hope you guys are too. So I'm going to pass it over to John with his talk about crypto pitfalls.
Thanks, Sean. All right, so I want to take a second to kind of lay out why I like giving this talk and kind of what the whole purpose is here. So I know, you're at B-side, so you have an obvious buy-in or interest in security. And what I've been finding as I go around is that I keep seeing developers and even security people in some instances make the same mistakes over and over with crypto, both in the news and in the organizations that I've worked with. And so this is really more of a cautionary tale. I personally love hearing stories about failure because I think those are the most fascinating stories and you can learn the most from them. And what I want is this talk to be grounded in real events. These are all real examples I try to give in most cases of like how it actually failed and what ended up happening when it did fail. My goal here is for a lot of us, hey, we're security people, but we may not be crypto security people, and it's very easy to get in over your head. So, knowing when you're in over your head and knowing when to get professional help is very important. So with that, I'll start the talk. As John mentioned, so I'm the security lead at Braintree. Braintree helps businesses accept payments online, businesses like GitHub and Uber and Airbnb. So as you can imagine, deal a lot with crypto, a lot with security. Something you may not know about Braintree, 2.5 years ago, we were acquired by PayPal. So as part of PayPal, if you've ever worked for a very large or a publicly traded company, you'll recognize this statement. These are my views, not that of my company. Yeah. All right, moving on, now that that's out of the way. So I want to start with a general overview of like what is modern crypto? What are we trying to get out of this? So in cryptography, in the modern sense, we try to get three things out of it. The first one's confidentiality. So this is keeping something secret. If I want to send something across the internet, like my credit card number, I want to make sure that it remains secret between me and the person who's going to receive it. That no one in the middle who intercepts it should be able to read it. The next thing is authentication. We also often call this integrity protection. And what that means is when I send a message, no one in the middle should be able to modify it without that being detected in some way. And then the last one, identification. We often combine this with the previous one. This is knowing who sent the message. So when I go and buy something on Amazon, I want to know that I'm talking to Amazon. So we often see this in the form of digital signatures, and that will say, John wrote you this message, and it hasn't been modified since John wrote it. Modern cryptography is a rigorous science. It's based on largely on hard math problems. So for example, RSA is based on the problem that breaking down a very large number into its base primes is something that we know is incredibly hard. That's the factoring problem. And what we're doing is we're betting on no major advances in either math or computing. So we know that RSA is very hard on classical computers. There's a whole subsection to be talked about for quantum computers, which you can go read about online because it's very fascinating. Crypto, like any science, should be peer-reviewed. So we often hear this in the war cry of don't design your own crypto, don't implement your own crypto. And I think we've done a really good job in the crypto community and the security community of getting that point across. Generally, it's very rare you'll find someone who disagrees with that these days. This also extends, though, to things like implementing your own crypto from like base primitives. It's very easy to not realize that you're making mistakes. Another thing with peer review comes up is Kirchhoff's principle. That is that I should be able to publish everything about my system and how the cryptography is used, except for the keys, and it should remain secure. We often think about this as security through obscurity. You shouldn't have to obscure the design of your system to keep it secure. So cryptography itself is very strong. The individual primitives, I wouldn't expect to see them break anytime soon. I don't expect to wake up tomorrow and read the headline, AES itself or RSA itself is totally broken. I do expect, however, to wake up and be like, the way TLS uses RSA and AES is totally broken in like some subtle way on these systems. Like that would make sense to me. It's because it's often the way we combine these systems. It's the seams that end up getting attacked. And that's really not any different from many other areas in security. We go after the seams where the systems are often the weakest. So I would like a chance to read this quote to you because I think it's really important and kind of sums up what I mean. This is from the book Cryptography Engineering. You've probably seen the door to a bank vault, at least in the movies. 10-inch thick hardened steel with huge bolts to lock it in place. It certainly looks impressive. We often find the digital equivalent of such a vault door installed in a tent. The people standing around it are arguing over how thick the door should be rather than spending their time looking at the tent. So what I kind of take from this and what this means is that, sometimes you'll find two people will be in this argument of like, it should be a 128-bit key. No, it should be a 256-bit key. And they're arguing about this aspect of a system, but they're not, ignoring the obvious like SQL injection or other, kind of attacks because it can be fun to argue about those things, but you have to make sure that you're not installing your bank vault door on a tent. So if you take nothing away from this whole thing, this slide I think is the most important for practical advice. Everybody, all these systems make these mistakes, but in general, what you would recommend is, hey, if someone comes to you and you're like, we need to protect data in transit, so that's data going across a network, use TLS. We used to call it SSL, or use SSH or IPsec or VPN. Use some known technology. Don't go and be like, let's go invent a new network transit technology. For data at rest, my general recommendation is use GPG. So data at rest means like data sitting on disk, data sitting on S3 or other cloud service provider. If you can't fit your model onto one of these two, try to rework it until you can, because it'll make your life a lot easier. The next thing I want to mention is to avoid low-level libraries. These are libraries like just OpenSSL, PyCrypto, Bouncy Castle. The reason is I often describe these low-level libraries as if you're giving a group of developers a bucket full of razor blades and you're asking them to make a saw. Someone is going to hurt themselves, and it's not, we can avoid it. It shouldn't happen. High-level libraries, something like Salt or libsodium, which has bindings to C, Ruby, and other things, or something like Keyzar, which is from Google, and Python, Java. I think they even now have C++. These high-level libraries help reduce the mistakes by taking away a lot of the seams. You don't get to make as many choices, and that's often actually a good thing. Choice isn't always great in crypto, so these help take away some of the choices and protect you along the way. So I did talk about I did promise pitfalls, so let's talk about those. The first place to talk about is random number generators. Randomness is a core part of any crypto system. We use it for encryption keys and session tokens and password reset tokens. So if we're not getting good random data, oftentimes that could be a very big problem. And so our first pitfall in this category, not using a cryptographically strong random number generator. There was a paper published at Usenix a few years ago called I Forgot Your Password, Randomness Attacks Against PHP Applications. And what they did is they surveyed and kind of dug into a PHP application that was using a not crypto strong random number generator. They were just using the built-in Mersenne twister generator. And they were using that to generate password reset tokens. And so with a little bit of investigation and digging, they were able to analyze the system such that they could predict correctly the password reset token that was going to be emailed to the user without getting it. And therefore, they could reset the user's password. And so this is kind of an example related to that. The data on the left is from PHP, some ancient version running on Windows, so it's kind of hamstrung into its worst case. And then the data on the right is from an actual random number generator that is correctly strong. And if you're at the right angle, which I am not, so I hope you are, what you see is the data on the left has a kind of a period. It has a little bit of waves in it, and that is the exact opposite of what you want in your random number generator. You don't want any kind of pattern at all. So the next one, using a broken random number generator. Since we're in the security community, we probably all hopefully remember the Debian issue a few years ago. If that predates your entry into the industry, I'll talk about it a little bit here. What happened was this line of code was commented out of OpenSSL only in Debian. So OpenSSL upstream didn't comment it out, but Debian is the base system for a lot of Linuxes these days. So this was copied subsequently into Ubuntu and a few others. It was commented out in 2006, but it was not discovered until 2008. And for 2 years, the random number generator in base in OpenSSL was broken on the Debian, and this had a lot of issues. So all the SSL keys and the SSH keys were broken for those 2 years, and they had to be completely thrown away and regenerated. And what this kind of goes to show is bad crypto looks a lot like good crypto, and it's very easy to get fooled there. So the commit message for this, the committer was, don't add uninitialized data to the random number generator. This stops Valgrind from giving error messages in unrelated code. So if you're not familiar, Valgrind is a utility to help analyze memory, like memory leaks and memory usage in C programs. They were essentially doing this to stop like a warning in Valgrind. And the sad thing is they ran this by the OpenSSL mailing list, and no one yelled like, oh my gosh, stop it, don't do that. I went back and did some research. Here is that line today. This is one way to stop people from commenting it out. There's giant warnings all around that doom will rain down if you touch it. But Debian was not the only system to have issues with random number generator. There was one on Android a few years ago where they found out that because their Bitcoin were being stolen, people who were using Bitcoin applications and digital wallets on Android devices. And what was discovered is that Android was shipping with a broken random number generator in its core OS. And this took quite a bit of undertaking for Google to fix. Another one, this was from very late last year. Juniper, it was discovered, had dual EC, which is a random number generator with questionable provenance that had been inserted in there, and there were constants in there that no one could really explain where they came from. And so that raised a lot of questions for Juniper as to why they stopped using a good random number generator and started using this dual EC. Especially because we've known since 2007 that dual EC is not exactly fast, and it also has a possibility that it could be easily backdoored. This presentation was from 2007 at a crypto conference. And this is one from last year. If you're following FreeBSD current, they were updating the random number generator in FreeBSD to follow a stronger model, and they accidentally broke it for 4 months. Fortunately, this never made it into a release version, but if you were running on current for 4 months, your random number generator in your operating system was broken. And then lastly in this category, I want to talk about not using random data when it's required. So in the PS3, they were using this algorithm called ECDSA, which is the elliptic curve digital signature algorithm. You don't need to know the details of it, but you do need to know that elliptic curve DSA, much like DSA, requires a parameter that has to be uniformly random for every single signature. So you would expect, I'll source this from a crypto-strong random number generator, but I believe in this case, Sony had a constant. They had hard-coded in the signing code. And this allowed, through some really fun math, the attackers to recover Sony's signing key. So they were able to sign arbitrary images to put onto the PS3. I think in this case, they used it to load homebrew software. So general recommendations out of this, use a crypto-strong random number generator. If you're on Unix or Unix-like system, read from dev urandom. There is some controversy about this that's kind of slowly going away. If you aren't familiar with it, I wouldn't worry about getting familiar with it. If you are familiar with it, we can talk tonight at the after party if you want to argue. Windows, there's random number generator in .NET, and there's CryptGen random for those who are on a Windows side of the house. Next up, hash functions. So hash functions, these are often called fingerprints, or they're kind of one way. The reason we think of them as fingerprints is just like ideally no two people have the same fingerprint, no two inputs to a hash function should yield the same output in an ideal world. And they shouldn't be reversible, meaning if I just give you a fingerprint off of a glass or something, without access to a fingerprint database, you shouldn't be able to tell me who that belongs to. And with hash functions, there are a couple pitfalls. The first one, using weak and old algorithms. So this was in 2008, MD5 considered harmful, which was one of the first considered harmfuls. In this case, they used a bunch of, I believe it was PS3s, to generate a hash collision in against a certificate authority that was still issuing certificates with MD5. So they were actually able to generate a custom certificate that had the same hash, or the same digital signature as a legitimate one, and they therefore got themselves a CA out of it. So this was the death knell for MD5 and the CA system. People basically told them, hey, you need to get rid of this, stop doing this, but they kind of waited until this happened before they were like, oh yeah, we really need to get rid of this. This was the headline after Flame. So Flame was one of those industrial systems malware that came out. I think it was an Iranian centrifuge that it was discovered on. And the kind of outcome of this was they discovered that there were previously unknown attacks against MD5 used in Flame to get it by Windows Update to like make it appear as if it was legitimate software. And this kind of goes to show you, it's like, oh, there must be some world-class intelligence agency that was involved in this because academia had no idea this attack was possible. And this is a very recent one. There are free start collisions in full SHA-1. This has kind of helped shuffle the CA system away from SHA-1 and certificates. We've moved past MD5 onto SHA-1, and now we're moving past SHA-1 onto SHA-256. But the CA industry is still very slow on this for a lot of reasons, but this paper is kind of helping move that conversation forward. This one's just a fun one I like to talk about. This is the logo for US Cyber Command. They apparently really like hash functions. If you're close enough, you can see on the inner ring, there is some letters and numbers. I'll blow it up for you. This. And so it's like, what is this? It turns out this is a hash digest. So this is an MD5 sum of their mission statement. I don't know why. This was many years after they probably should have been using MD5. But yeah, so crypto as a design aesthetic too. The next thing, misunderstanding what a checksum is. So this is a directory that you could have pulled off like an FTP server or whatever. And this is all fine and good, but what the misunderstanding is sometimes is that folks will download the SHA-1 sums or SHA-256 sums file, and they'll compare it against their downloaded file, and they'll go, this file hasn't contained any modifications. But what it really is showing is that it didn't get corrupted during the download, because any attacker who could replace one of these files could just as easily replace the checksums file because there's no additional like GPG signature on it or something. So that's just something occasionally I'll see folks kind of still make that leap mistakenly. And then the last one I want to talk about here is length extension attacks. But before we can do that, I have to talk about what they're actually going for here, which is something called a message authentication code. So a message authentication code is kind of a class of functions in cryptography that takes a key or a shared secret and a value and returns something we call a tag or an authenticator that represents the integrity. And ideally what this shows is that if I send a message across the wire, anyone in the middle who doesn't have this key and they modify the message, the outcome of this tag will kind of show if they've modified it because the tag will be different. And only two people who share the key can kind of validate the tag appropriately and create new ones. So this is great. And a naive approach would be to create it just like this. So we'll take the key and we'll concatenate it with the value and we'll run it through SHA-256. So the problem here is that SHA-256, like almost all of the hash functions we use, besides some of the newer ones, have a construction where they're vulnerable to something called a length extension attack. This is just kind of in the basis of how they're designed. So here's the example in code. I take my secret and my value and I concatenate it, and that's my signature. And what this allows an attacker to do is, without knowing the secret and without knowing without really even knowing the initial value, they can put arbitrary additional data at the end if they can get you to kind of do the thing. So this, here it's like buy 10 units at $1, and then it's like actually make that 0. You can like change the semantic meaning of the value you're trying to hash. And this is, once again, without knowing the secret. So what should have been done here is they should have used a function like hmac or another secure MAC function, and that actually prevents this type of attack. There are newer hash functions like the SHA-3 competition that explicitly in their design criteria said that you had to defend against this, that you couldn't allow this type of attack into your hash function, just because they know that down the road someone's going to once again forget this and try to design a system like that. So this isn't like oh, that's cool. This is a practical attack. It was used on Flickr's API a couple years ago, and so they've remediated this. This is from this year, though. Visa released a new payments API, and in it, they were doing the exact same thing, key concatenated with data, and so in their documentation of a just released service. Fortunately, they have now since fixed this, but that kind of goes to show you that like we are doomed to repeat a lot of these same mistakes if we're not vigilant about them. So use SHA-256 if you need a hash function or checksum. Use HMAC version of that if you want an HMAC or a MAC or a signature. Stop using MD5. It's very difficult, but you should really start to move away from it. And don't use SHA-1 in new projects. That's not a like, hey, we need to run out and change SHA-1 today. Unless your project's using it for collision resistance, then you should probably move a little bit faster because these things take a really long time to migrate away from. All right, so no crypto pitfalls talk is complete without talking about password storage. Briefly, I want to talk about, hey, we've had a lot of breaches. So this was the original LinkedIn, but it turned out it wasn't 8 million, it was 117 million. And then Last.fm, Yahoo, Dropbox, eBay, Slack, and MySpace. So, and there are unconfirmed reports about Twitter as well, but I didn't want to put those in here since they weren't confirmed. So we, as an industry, we know that these password databases are getting out. And fortunately, most of them don't do this. Some of them did do this. So a naive way to store a password is, well, I guess the most naive way is to just store the password, which some systems still do, just the plain password. But the naive approach is to do the SHA-1 of the password. So this does have a positive. It's a one-way value. It can be used for verification. But that's really its only benefit. So then the architect will say, we should salt our passwords. And so they'll do a salt of the SHA-1 salt plus password. And so now we're catching up to like where Unix was in like the late 70s, early 80s with this system. And so this also has another benefit. It's randomized. It can largely defeat these pre-computed tables, the rainbow tables. And it forces attackers to focus on one password. The problem is these hash functions are incredibly fast because that's their design. They're meant to be fast because you want your TLS connection to be fast. So what we actually want one is that can be adaptively slowed down. And so those are called adaptive hashing functions. There are a bunch of them out there. I honestly don't care which one you use as long as you're using one of them and you correctly tune it so that it's as slow as it needs to be. So bcrypt, scrypt, argon2, pbkdf. Argon2 is like the new hotness on the street because it won the password hashing competition. So my recommendation is delegate your authentication if possible. Facebook, Twitter, Google, GitHub, they all allow you to delegate authentication to them. And if I want to comment on your blog, I don't think I need to give you a username and password to comment on the blog. You should delegate your authentication. There's no reason for you to have passwords. And then otherwise, if you have a system where delegation doesn't really make sense, store one-way verifiers using one of those algorithms. So I know some of you out there are thinking, well, I know we have a system that uses SHA-1 with assault. What are we going to do? It's just inevitable. Like we wrote code before 2010. Like that code still runs in production. There are still systems out there like that. So it's okay. You can fix it. I promise. My recommended way to fix it, I'll present it. Generally, what people do here is, so say you have a password hash function that's just the salt concatenator, the password to like SHA-1. So the naive and kind of common approach is wait for the user to log in, and then we'll like silently update their hash in the background for them. And that's great, but have you ever looked at the statistics about how many users actually log in and when was the last time they logged in? And what you'll find is there's an incredibly long tail. In most systems I've seen, I would be surprised if more than 50% had logged in the last month or so. So don't wait. My recommendation is if you have a reasonable system that wasn't as incredibly bad as something like Descrypt, which, if you don't remember, Descrypt cuts passwords off at 8 characters. So just wrap bcrypt around the existing system, and then your system becomes bcrypt of SHA-1, and upgrade all your passwords in place, done. Because users who don't log into your system deserve password security as well. So password hash column is now bcrypt of SHA-1 of Salta password. And as long, this is generally reasonably fine. If you want to migrate them to just bcrypt as they log in, that's fine. But at least your users who don't log in will be in a better position. Next, let's talk about some cipher pitfalls. Once again, old weak algorithms kind of rears its ugly head. So this is a paper from a while ago. I think this research was sponsored by the EFF back in the early, like the mid to late 90s. Breaking ciphers with Copacabana. This was one of the first, like, hey, can we use FPGAs and like custom-built hardware to break systems? So this broke DES, the original DES, not triple DES. And the numbers in this are fascinating because you could do it for far cheaper today on Amazon. Next one, so we've known for a very long time that RC4 was not a great cipher. There are weaknesses in the key scheduling, there are biases in the output, and yet it's still like a very well, kind of very widely used cipher on the internet. So then there's a vulnerability in a movement called RC4 No More, trying to get systems to move away from RC4 because it still is available in TLS today. So if you have a block cipher using ECB or electronic codebook mode, to kind of talk about this one, we'll need to do a refresher on what is AES and what are block ciphers. So block ciphers are a pair of functions. They take a key, and then they take either the plain text and the ciphertext, and they give you either the plain text or the ciphertext as the output. With me so far, I hope. But the plain text, or the input and the output, are 128-bit values. And I don't know about you, but most of my data is more than 16 bytes. So what do? What people generally will come up with is we'll just loop over it 16 bytes at a time, and we'll encrypt it that way. So this is a formalized mode. It is known as electronic codebook, and it has many problems, but one of the main problems that is basically easy to talk about and easy to show is it allows patterns to show through your output. And so if your input has any kind of structure, you'll see that structure come through in the output. So this is the Braintree logo, and this is the Braintree logo encrypted in ECB mode with AES and some random key. So you may have seen this with the Tux the Linux Penguin, but it's the same idea. What we actually want is the thing at the bottom. We want, it can look completely no different than noise, and only with the correct key can you kind of see what the true meaning was. Like I said, there are many other issues with ECB mode, but this is the one where it's like people can kind of, when you visualize it and can see it, a lot of folks will get it. Not using authenticated encryption. So this one, so we've known for a very long time, since Eurocrypt 2002, Downey pointed out things called padding oracle attacks. This paper came out in 2010. These were the folks who did the Beast attack on TLS, where they actually made this practical, and then later on, folks redid it with a different part, and they made Poodle. So practical attacks that have come out of this paper. Another one, Lucky 13, which was another attack against TLS. This is where code wasn't constant time, so it leaked information. And then lastly, this one's very recent. Apple had an issue in iMessages where they weren't using authenticated encryption. And we kind of know these days now that, remember at the beginning we talked about confidentiality and integrity. We know that if you don't provide integrity, you can't guarantee confidentiality. So a system has to have both. And that's what we mean by authenticated encryption. So this was the paper that came out of it, out of Johns Hopkins, Dancing on the Lip of the Volcano, Chosen Cipher Attacks Against Apple iMessage. And largely, I don't blame the developers. Like we've kind of, as security professionals, we've given them this world of hurt that they live in. Like this is the documentation for PyCrypt, the the Python crypto library, and like look at all these options we've given them. Look at like all these things they have to choose, and then you can't see it, but in this example at the top, they're using CFB mode, which nobody uses. Like why is the example in the documentation using an encryption mode that A isn't authenticated encryption and B no one uses in practical systems? Like we're kind of really just setting folks up for failure. So my recommendations: prefer the secret box constructions from Sodium and Salt. Stop using DES. Like really, if you have a system that uses DES, you really should. As soon as my talk's done, you should probably go to your office and be like, "What's our plan for migrating away from this very soon, like this week?" Stop building your own on top of AES if you can. Stop encrypting without protecting the integrity. So here's my slide for anybody who's in a regulated industry. So what if you have to use AES? What if your auditor comes to you and says, hey, you didn't say AES when you were talking about your encryption scheme. What's this thing you're talking about? You didn't say the words AES. Don't use ECB mode. Be sure you're using authenticated encryption. So GCM is kind of the go-to for authenticated encryption with AES. There are other alternatives, though. Verify the tag or the MAC before you decrypt something with GCM. A lot of good libraries will do this for you. And then it's still easy to mess up in a critical way, unfortunately. Let's talk about some TLS or SSL. So hopefully most people will have known that we used to call it SSL, but then it's been superseded by something called TLS. And the SSL itself is no longer in practical use, at least since Poodle. A lot of systems may still have it enabled, but you shouldn't. Everything should be using TLS now. So the first thing, not verifying the certificate chain or the host name. So this is a pretty big one. There was a paper a few years ago called The Most Dangerous Code in the World, validating SSL certificates in non-browser software. And what these researchers did is they kind of did the survey of all these mobile apps and things like that to say, hey, were they doing TLS and SSL verification correctly? And boy, did they find out no. So outside of browsers, most systems weren't doing a very good job. And so what is involved in verifying that? So if you're not familiar with the certificate chain, it's kind of this thing at the top that I've highlighted here. And that's where it says, hey, I have this certificate for Braintree payments. It's trusted by this other certificate, which is trusted by this other certificate that we have installed in our operating system already. The other problem is that hostname verification is, it's not built into OpenSSL, so a lot of applications aren't doing it because they thought OpenSSL was just doing it for them. And that's checking that you got the certificate for who you intended for. So the first one is checking that the math is correct, so the certificate chain math is correct. The second one is just checking that the string of the domain name is the one you intended to connect to. If you don't do the second one, I could just go get a free certificate from Let's Encrypt, present it to you, and you're going to think that it's valid because you're not checking that the subject of it is who you're actually intending to connect to. So what does that look like? It looks like passing -k to curl, which I honestly have seen in a vendor documentation. They're like, just pass -k. It means like secure. This is some PHP code because I'm picking on them. So if you use curl, verify peer is like, hey, I want to know who I'm talking to, and then verify host is like, I want to make sure that they say who they are who they say they are. You have to have both. In some instances, one or more is set to 0, so it's not actually doing the verification. Misconfigured server settings. So this is the report from SSL Labs. The identity of the domain has been blocked out because I didn't want to embarrass them too bad, but needless to say, this was a government-oriented website in the EU. And they got an F, and there's a litany of issues with it, like using weak Diffie-Hellman, untrusted certificate, like a bunch of stuff. If you haven't already, use SSL Labs to run it against your servers. It's an incredible tool. It will give you a very, very good overview of like what you're doing well, what you're not doing well, and then links to how you can improve it. If you're totally lost for where to start, Mozilla has released a tool on GitHub called the TLS Server Settings, where you basically like, I'm using Nginx, I'm using OpenSSL here, and it just like spits out configuration for you to copy onto your server. And then the last one, using a broken library. So we all remember Heartbleed. I'm sure a system after this talk is still going to be compromised because no one patched for Heartbleed. GoTo was another one. OS X and iOS share some crypto code, and that crypto code wasn't validating part of the TLS handshake correctly, so you could intercept and modify traffic bound for those devices. So ensure you're validating your connections, like go and actually check and like double check. Lean on a framework and library. Check that it does the right thing though, because sometimes they don't, and no one told them. Set up automated tests to validate this setting. So go to like badssl.com and see the examples of all the bad forms of SSL and TLS that they have in there. So lastly, I want to talk about trust. Quick poll. How many people have seen this prompt before? You know what this is. All right. Now keep your hand up if you validated that fingerprint before you typed in yes. There are honest folks in the audience. Thank you. So what this is SSH has a trust model called TOFU, trust on first use. And what this means is that SSH is kind of like, hey, we're buddies. You tell me if this is cool, and then I will mathematically check that it's the same always after that. Hopefully, I'm sure people have seen this. Hopefully you didn't just go blow away the entire known host file. That's generally the Stack Overflow response for like what to do with this. This is saying, hey, remember that thing I promised you I would do? I'm doing it. This mathematically doesn't check out anymore. Usually this means like someone reinstalled the operating system or something. So this is a video of me scrolling through all the Mozilla trusted certificates that ship in Firefox. You're not meant to follow it because there's a lot of them. So what I ask is, like, do you trust all these organizations? Do you trust their hiring, termination practices, their audit practices, all these things? I imagine you probably don't. There are some organizations in here like the Hong Kong Post Office, the Department of Homeland Security, Visa. So while some of them are trustworthy organizations, I'm sure, and you have to trust somebody, it's always good to like take a step back and think about, who do I trust? Who in this organization? Because my old list, this list I believe is up to date, but the old list included organizations that had been breached, like DigiNoider. And that brings me to the last topic of certificate pinning. So certificate pinning is a way for you to kind of narrow down the trust for your application. And that allows you to kind of choose my application. We use trusted roots, but we're only going to trust these few. Or you can even go further. It's like, I'm only going to trust this key that I know we generated, ourselves. There are multiple ways to do this. The emerging way for web browsers is this public key pinning proposal. I recommend you go investigate this. Find out if it's appropriate for your application. So think about what organizations you really trust. Investigate certificate pinning. All right. Is it over? It is over, Stephen. If you want to learn more, I highly recommend the Stanford crypto class on Coursera. I don't believe there's a currently scheduled session. They pop up from time to time. There's also a part 2 to this class that I like to describe as the Bigfoot of Coursera classes. Everybody keeps saying it's coming. I heard it was coming in the fall, and then it never happens. And then one time they sent out a course survey, a pre-course survey for it, and then that went away. It's kind of crazy. I am looking forward to it though, because it was an incredibly good course from Dan Downey. And then lastly, the Matasano crypto challenges from CryptoPals. This used to be run out of email. They would email you the set, and then you would email it back. They get very overloaded with email, so they set up a self-driven website. So these are kind of developer challenges where you actually get to write code to break these crypto algorithms. It's really, really cool. And that is it. I have 4 minutes for questions. Thank you.
All right, so I have a quick question.
Yeah.
Earlier in your slides, you gave some recommendations, and you said SHA-2.
Yes.
I was wondering why you didn't say SHA-3.
I will answer 2 things because you said something and I wanted to help people. So SHA-2 applies to a family of functions. SHA-256 is one of that family. Why I did not say SHA-3 is because it is not, although it is standardized, there are multiple reasons. A, you don't find it implemented in a lot of systems yet, so you don't find access to it in like the libraries. And then B, there were some like last minute shenanigans with it between it and NIST and the other organizations that have people kind of going like, hey, we had this perfectly good algorithm, why did you mess with it at the last second? There are other great hashing algorithms out there, Blake 2 and a few like that, that were finalists in the SHA-3 competition. I personally, until we have a reason to switch, SHA-256 is still a really good choice. SHA-3 does have like the length extension thing is fixed and a few things like that. But honestly, the systems I work in, we don't have access to it unless we add like native extensions or anything. So it's like not even surfaced yet. They are, and so he said functions are awesome, and that is true. And there's a lot of future use of them, but we have to actually have practical like applicability.
Hey, so you talked a lot about the server side. Can you say quickly, like from the browser side or from the website? I know you talked about certificate pinning and trust, but what, as an end user, can I do to kind of protect myself?
Yeah. So the question was, I talked a lot about the server side. What about the browser, the client side? So SSL Labs has a client side test too. That you can either, I think you can either curl it or you can like whatever your system, go fetch it, and you can hit it with your browser, and it'll tell you if it thinks your browser's doing a good job. There generally aren't too many knobs in the browsers for you to choose, at least for the most part. I think the best advice is keep your browsers up to date. So Chrome, Firefox both do an excellent job of keeping up to date, and Chrome even so much as like when they have issues with certificate authorities, they'll push blacklists out, and like, you know, that's their kind of their big hammer for certificate authorities is like, we'll block you, which totally cuts off your commercial viability because that's a major browser.
Yes. So this is an interesting question. Do you feel that transport layer security is sufficient, or with things like sample requests, do you feel you should be layering on top of things like XML encryption in addition to transport security?
Okay, so the question was, do I feel transport layer security or TLS is sufficient, or do you need to layer additional things on top of it? You mentioned SAML and then XML encryption in the payload. So for that, I have that conversation with a lot with engineers in my organization, and I think in each case it comes down to like, what's your threat model, right? Is your threat model, someone will fat finger it and unencrypted data will get dumped out to logs or Splunk or something, you know, and then, you know, then we at least have an encrypted payload there instead of an unencrypted payload. I think largely the wrapping an encryption around an encryption, that means at some point you don't trust the person unwrapping one of the encryptions. So figure out why you don't trust them, and if you still don't trust them, that's fine, like layer the encryption, but it's important to think about it from a real threat perspective.
Who's your favorite, RS or A?
So the question was, who is my favorite RS or A? So Ravesh, Samir, and Edelman. True story, I was at the Real World Crypto Conference, and I hope no one ever watches this on video. I saw Ron Ravesh fall asleep in the front row of the thing, so he has to be my favorite. He's like, I am so OG, I can fall asleep in the front row of this crypto conference.
You mentioned some federated off, like OAuth, like Facebook and Google. Do you have any thoughts on FIDO, ETF for UA yet?
On FIDO. Yeah, so the question is, do I have any thoughts on FIDO? So I'm a big fan of FIDO. PayPal, my company, is also a big proponent of FIDO. I was one of the first people to buy the U2F and like start implementing it. And I'm actually really sad because I was like, I'm going to do a Ruby gem that does U2F. And I started writing it, and I got very far, but then I got like distracted. And then like 2 days later, someone pushed a empty gem and claimed the name, and I was just like flipped the table, and I was like, never mind. Hopefully they finish it. But yeah, I'm a big fan. Look into FIDO, the U2F, and the UAF frameworks. Those are cool. All right, I don't see any more, but I'm also have lights in my eyes, so thank you.